Hi, welcome to Mastering GCP Landing Zones. I'm David Morpurgo, Senior Site Reliability Engineer at Lufthansa Systems and part of the network team.
Hi, my name is Simon. I'm also a Site Reliability Engineer, background in cybersecurity, and currently taking care of GCP and automating all of that stuff with Terraform into some nice pipelines.
So, my name is Armin Berberovic. I'm a security architect at Lufthansa Systems. I mostly work with clouds and everything related to it, and I like to share my experience at heise.de or at my personal blog, cloudsec42.com. So, a few words about my employer. So, Lufthansa Systems is an IT solutions provider for the aviation industry. We were founded like 1995, and our headquarters is located in Raunheim. So, if you don't know where Raunheim is, it's close to Frankfurt. We have like 16 branches. We have branches in 16 other countries, and we are 100% subsidiary of the Lufthansa Group. So, but you're not here to hear about me or to hear about my employer, but to hear about landing zones. So, what is a landing zone? To put it in one sentence, it's a ready-to-use platform where you can develop and run airline applications. So it comes with connectivity and security built in. It has a governance framework and processes around it. It comes with 24/7 support. And even that today we are only talking about GCP. This is a multi-cloud solution that spans GCP and Azure. So, well, I myself am a security guy, so I like to talk about security topics. And today I want to talk about environment isolation. So why do you want to isolate environments? Like two reasons for that. First of all, it reduces the blast radius. That means like if one environment goes bad, the other ones are still intact. The second thing is it improves collaboration because as you isolate environments, you remove dependencies so people can move more independently from each other. So how do you do isolation in GCP? So it all starts with a folder. A folder is basically one environment where you can put all your resources in. So you want to have two environments, you create two folders, put the resources inside, and then put some ERM policies on top, and you're done. Simple enough, but how can we get this isolation we have in the cloud to the GitOps world? So how can we get it to the pipelines? And this is what I want to talk about today. So let's start with an example. So imagine you have two teams, a network team that's managing firewall rules and developers that are like developing and maintaining applications. And because you're using GitOps, of course, they're doing everything in code. And now you want to put all of their code into one repository. So you basically use a monorepository. If you have that set up, how can you ensure that developers cannot modify firewall rules? Because this is what isolation is about. Okay, so let's look at the setup. So this is the setup of the monorepository. On the left side, you can see the files contained in it, like multiple files, and one that is called firewallrules.tf. At the bottom, you have a code owners file that sets the networking team as the code owners of this one particular file. So if you're not familiar with code owners basically define who must approve changes to that file, and only they can approve them. And the last picture shows a simple firewall rule that just opens the SSH port to the whole internet, something you usually don't want to have. So let's look how a happy path would look like for that isolation. So let's say you want to add that firewall rule. So you go ahead, you put it in the firewallrules.tf, then the code owner kicks in, and depending on the review done by the networking team, either it's discarded or it goes into your live environment. So what could possibly go wrong with that? And the answer is basically everything. So first of all, like there's literally no reason to put that firewall into that piece of code. You can put it anywhere else, and effectively bypass code owners. So if you now misconfigured your pipelines, this change will happily go into your live environment without ever seeing the eyes of anyone related to networking. And that's something we don't want to have. So let's investigate why this is happening. Okay. So to understand that, we need a model of a pipeline. And this is a really simplified view of a pipeline. And it all starts with a user adding a change to the code base. If that change makes it successfully to the code base, a service account is picking up that change. And if he has the correct permissions on the live environment, he will go ahead and do the change in the live environment. So in this case, in GCP. So this is an other view of what I have just showed you in code. So we can see the happy path and we can see the attacker's path, like the developers doing the firewall rules in it. So let's start with the happy path. So there's a person from the networking team that adds a change to the code base. It gets reviewed, it gets merged. The service account takes that change, looks into it, sees it's a change to the firewall. So he goes to the networking folder and modifies the firewall. All is expected. Now, if a developer goes and puts the very same change in, the service account will again pick up the change, look into it, see it's a modification of the firewall, go to the networking environment and change the firewall. And this is something we don't want to have. And there are two reasons why in this configuration the pipeline is behaving that way. So first of all, is on the far right, where you have to give the service account access to both environments. And you cannot avoid that because he must be able to do changes of either team. And the second thing is that the service account doesn't really know where the change is coming from. So like, to put it in other words, he lacks context. And this is the core message of my talk, like context matters. So what do I mean when I say context? Let's look at this GitHub Actions flow and go shortly through it. So it starts with authenticating to GCP. We can specify a service account, and the ID of the service account is actually sourced from a GitHub repository variable. Next, the code is checked out to the runner, and a Terraform init and a Terraform apply are run. So when I talk about context, I talk about what service account runs Terraform apply and what permissions that he have. Because this is the core security boundary we have here and that we have to respect. So now to answer the question from my first slide, how do we isolate, how do we bring that isolation from GCP to GitHubs? We discarded the idea of a mono repository. Instead, we switched to polar repositories and we use a repository per environment pattern. And the important things about this is that we have like 2 dedicated service accounts, and each of them only has permissions to what he is allowed to modify. And if you recall just the actions file from the previous slide, we sourced the variable from we sourced the ID of the service account from a GitHub variable. So we can in all repositories reuse the same workflows file, just modify the variable, and by that way ensure isolation in our GitHub's pipelines. Okay, so that's from my side. I will now hand over to my colleague Simon Kohl, and he will speak more about pipelines.
All right, thank you, Armin. All right, let's talk pipeline automation a little more and see how these pipelines work from our code base to the actual changes in our GCP environment. Of course, we're starting out with a code base. For us, this looks something like this. Of course, we have a lot of Terraform files in there, and also a lot of YAML files we use for configuration. We chose YAML here over JSON or HCL files because we feel like it's just a little more human readable. And this also allows people without in-depth Terraform knowledge or in-depth knowledge about our setup in particular to work with the environment, extend it, add new entries, add new customers. So this kind of works out for us really well. However, YAML files are not supported currently by Terraform natively as input variables, so you either have to use the YAML decode function, which we use at some places, or you convert it to a JSON file, then you can just use it as a TF-vars files as usual. So both ways work out. This code is then, of course, committed into version control. We make heavy use of GitHub in our setup. So yeah, everything is committed into repositories at GitHub for us. And for committing stuff, we are specifically using signed commits, because usually the repositories we are working with are really powerful. They can build up things, they can destroy existing things, and hence we really want to make sure that we have a non-disputable history of what happened at which point in time and who actually did it. Let's also make sure that no unsigned commits are smuggled in there. Then, if you commit things, you can commit it to the main branch, which is usually the branch that actually deploys resources to our environment and makes changes happen. This branch in our setup is basically 100% of the time protected, so you cannot commit directly to that branch. This also prevents the branch from being forced pushed to. Again, preventing somebody from erasing history. So this again makes sure that we always have a history and we can always hop one step back once something goes wrong in any unexpected way. And if you want to make some changes to the actual environment, you have to create a feature branch, push your changes in, and then do a merge request or pull request, depending on your platform, which then somebody has to approve. As Armin just mentioned, this is controlled via code owners. You can prevent changes to specific files without the approval of certain people. So this also comes in really handy if you want to, for example, allow people to do changes to the configuration files, but not the Terraform files. So then, once you commit some changes to one of those branches or merge a branch, this kicks off a GitHub workflow. This can also be like any other CI/CD tool of your choice. As I said, we are using GitHub for that. And once these pipelines run, they run, you guessed it, Terraform, of course. In GitHub pipelines, this looks something like this, just having a YAML file with these 3 steps in there. Obviously, you recognize these 3 lines. That's the usual stuff you also run on the CLI. So anybody who can run this on CLI can also easily automate it. And we are doing for the feature branches, we are doing the Terraform plan stage, even though the stuff is not merged into deployment branches where it would actually make changes. But before that, we just run the Terraform plan stage. So the developer who proposed the changes and committed them gets a preview of what this change is about to do. And it also ensures that a second developer also checks the commit, checks the Terraform plan, and can catch any errors that the first developer may have overlooked. So this makes sure we have a 4 eyes principle here on any changes that really hit production, before they hit production, of course. And once you then merge something into your main branch, or which is the deployment branch, however that branch is called for you, we also run the Terraform apply line, which then brings our changes into our Google Cloud environment, ultimately. As Armin has mentioned, we are running several repositories, like a lot of repositories that focus on specific partitions of our infrastructure. And as he already mentioned, you need service accounts for Terraform to use to make these changes in your environment. And as we have a lot of repositories, we would have to use a lot of service accounts too that Terraform can use. So we would have to juggle really a lot of credentials and or use one very powerful credential for all of the repositories, but obviously this is a very bad idea. So the question here I want to really emphasize is, how does this access really work? And how can we make it as good as possible and reduce the effort? So in a usual setup, you would have your code base and your CI/CD software that would run Terraform and apply the changes to Google Cloud or whatever you're using here. And on the way, somewhere pick up a service account key or any sort of token that grants access, any sort of secret that grants access to the service account you're using. However, this is still a static secret that has to be stored somewhere. Usually, GitHub Secrets is an option for that, or whatever you're using here. But still, this is a static secret, and static secrets should be rotated every few weeks or months, and they could be stolen at any point, misused for other purposes. So there's some inherent risk to that. So let's see if we can do this a little better. So fortunately, there is another way to do that. That makes the entire pipeline look a little bit more like this. So you have the CI/CD pipeline basically that runs Terraform and directly does the changes in GCP. But of course, you notice here that there's no secret anymore. And this is possible through a mechanism called Workload Identity Federation. And this works by basically pre-establishing a trust relationship between an identity provider, GitHub is one, you may use anything else you like, and GCP. Yeah? And this creates a trust relationship between the two. And this leaves us in a scenario where there are no secrets to manage, no static secrets at least, that is. And this relieves you a little bit from the burden of having to manage and rotate secrets and store them like close to your code base. So how does this work in detail? Whenever a pipeline is kicked off, for example, for us it's GitHub again, yeah. Whenever a pipeline is kicked off, GitHub submits a chunk of information about the identity of that pipeline to GCP. And this chunk of information contains information such as the repository name, the owner of the repository, the branch, several other details, and also contains a line about the service account that this pipeline would like to run as. No secrets involved yet. Only the service account the pipeline would like to run as, including also a GitHub signature that really makes sure that GCP can validate that this chunk of data is really genuine, hasn't been tampered with. You know the deal. And if this identity details then match certain predefined policies, we will talk in a second about that, certain predefined policies on your Google Cloud platform, Google will go like, all right, looks good to me, here's your token, and return an access token to the requested service account to the workflow. Do note here that this token is a temporary token, so it's usually very, very short-lived, less than 10 minutes. You can specify that yourself, whatever fits your need. But this token is really short-lived, so even if somebody was to steal it at some later point, it's probably already expired, and hence pretty worthless. So how can you set this up, and how does it work? The first step is just configure your ID provider on the GCP side. So this effectively establishes the trust relationship between GitHub or whatever provider you're using and your GCP platform, and makes GCP trust the information it retrieves from the identity provider. Second thing, and this is the interesting part that restricts access, this is the policies I've been talking about one slide earlier. You select the service account the pipeline should run as. And you then grant the role of account token creator to an identity. And this allows this identity, the role is granted to create access token for that service account, so impersonate the service account and act as their service account. This is exactly what we want. But instead of just entering a usual like email address or regular identity there, we use that string that looks a little URL-like. It starts with principal set, has some static information that is always the same. But the really interesting part is in the end, where you can see like attribute repository, your repo name. This is a restriction we can place that restricts, this is what we mostly use, based on the repository name, which repositories, which pipelines from which repositories are allowed to impersonate the service account. And after that, you're basically already done. For GitHub Actions, there's a pre-built action by Google. You can just plug this into your pipeline, specify the workload identity provider. You set up in step 1, place the service account you would like to impersonate. And yeah, this step then performs all the handshake magic from a couple slides earlier and places the credential file in your runner environment. And Terraform will then use this credential as if you had an already authenticated G-Cloud session in the background, so no further configuration in Terraform is needed. And this eventually then relieves us from having to manage any static secrets in any of those repositories and makes the approach a lot better scalable, because then we can have a lot of repositories. They are all able to authenticate without any static secrets in those repositories. So, and that's it about Workload Identity Federation and how the pipelines work. And I would hand over to my colleague David for the networking part.
Thank you. All right, let's talk about the network. On a very high level, we decided on a hub and spoke topology. We run Palo Alto firewalls at the core. We use Partner Interconnect and Megaport to connect to DCs and other cloud. We isolate customer environments in shared spoke VPCs that are peered to our hub, and we attach service projects to them. Let's look at the details. You can see we have 2 Palo Alto VM500s. Each has 8 VPCs they're attached to. So 8 NIC per instances, 16 interface IPs, load balancers, cloud router, and we have a lot of routes and policies. That is a lot of resources. And these resources only make a working landing zone hub if they're correctly configured. So imagine building this without Terraform. In the ClickOps days, we would have no way to find out why and when and by whom a change was made. Issues could be introduced during troubleshooting. You would be almost guaranteed that clone deployments would be slightly different. And if you were going multi-cloud, you had to learn each CLI or UI cloud interface. That's why we love infrastructure as code. In the network team, we maintain one code base with which we deploy 6 identical production instances. We can deploy a new one in 5 minutes. We have auto drift detection to make sure that the running infrastructure matches the codified one. And we leverage the powerful GitHub's change management workflow. Let's look at how we onboard the customer. We have a network project factory repo where we can add a few lines of YAML to define a new project that will host the shared VPC for a customer. We can define to which hub it is attached to. We can define the service projects. We make a pull request, and on merge, all the necessary resources are created automatically, and there's no manual steps. That includes the GCP project, the GitHub repo, service accounts, AM bindings, workload identity federation. Additionally, this new GitHub repo is created from template. And the template already includes the GitHub action file and the action variables, and also the code in Terraform to create the shared VPC. We just have to go to this newly created repo, add the subnet information, pull request, merge, Terraform apply, and we created a new shared VPC. We onboarded the service project in the shared VPC, and we paired it to the hub. So coding the landing zone took us a while, but deleting the prototype didn't. When building cloud networks manually, one would leave the prototype running for a very long time after it was in active development, just in case you wanted to check something. With Terraform, all the knowledge gained by development is in the code. So when we're done actively developing something, we can just Terraform destroy, save on cloud builds, and if we need it again, we can just redeploy it. Finally, when onboarding infrastructure as code in the networking, there's some things we have to take care of. Networks have to be run, and so if you build networks in code, they need to be supported also in code. Changes can be made on the live infrastructure, but should be then put into code, otherwise they would be reverted the next time the pipeline runs. So you should make sure that your support team also speaks Terraform. And also, you probably won't be able to get everything in Terraform from the start, and that's okay. Established internal processes and limitations on third-party providers might mean that you might have to do some things manually for a while. Changes take time. So for us, firewall management is still largely within Panorama as a manual process. And I hope to talk to you about next time on how we migrated that to code. So that's all for us. Thank you so much for listening. Come and catch us around if you have any questions about our talk. And yeah, thanks again.